Hello. In this video, we're going to do a quick primer on rotational angles. By no means is this going to be an exhaustive lesson that covers everything you need to know about the topic. But the purpose of this lesson is currently students are looking at sine law and cosine law, and we are in what's called the ambiguous case of sine law. And what the ambiguous case is, it's an angle side-to-side case where, in fact, we can draw two triangles. And when you pull out your calculator and you work through the answer, you'll end up getting an answer for one of the cases. And your calculator will always give you the acute angle. So to find the obtuse angle case, what we do is we take the acute angle and subtract it from 180. And of course, students inevitably ask the question, well, why do we do that? And in order to understand why we do this, we have to understand something called rotational angles. So this short little video, well, it might be a little more than short, but I'm going to try and explain why we apply this 180 minus the acute angle to get the second case. So let's dive in. So you should already be aware of your primary trig ratios, working with a right triangle, and often people will learn this acronym, SOHCAHTOA. So sine theta is the opposite over the hypotenuse, cos theta is the adjacent over the hypotenuse, and tan theta is the opposite over the adjacent. That shouldn't be a problem. What we see occasionally when we're working is sometimes we'll start seeing things like this. We'll see sine of 150 degrees. And again, we learn that primary trig ratios come from right triangles. But maybe we take some comfort in the fact that an angle in a triangle can be 150 degrees. So I type this in my calculator and I see that I get an angle, a ratio of 1/2. That's fine. So then maybe I've seen something like this, sine of 510 degrees. So now I really kind of stop and pause for a second, because there's no way that a triangle can have 510 degrees in it. But I plug it in my calculator and my answer is 1/2. Now I've picked these two angles very deliberately, knowing that I'll get the same ratio. So if my primary trig ratios come from a right angle triangle, the question is, how do I visualize a right triangle? So in other words, how do I take 150 degrees or 510 degrees and set up a right triangle so I can identify the opposite and the hypotenuse? And this is the same thinking for cosine and tan. And this is what we do. What we do is we take our triangle and we actually place it onto a Cartesian plane. So what we do is we create an XY plane. And so we remember that the horizontal is the x and the vertical is the y. And we take this triangle here and we place it like this. So we put it into quadrant 1. Remember, this is called quadrant 1. This is called quadrant 2. This is called quadrant 3. And this is called quadrant 4. And I imagine that I create the angle theta by starting at the positive x-axis and rotating in this direction all the way until I've created that angle theta. And then I go from this xy point here and trace a line straight down, a perpendicular line with the x-axis to get my right triangle. And at this point we introduce a few new pieces of terminology that we need to know. The positive x-axis, write this right, positive x-axis is called the initial arm. This is where we always start the measurement of our angle from. Where the arm stops is called the terminal arm. So if I want to create an angle of, say, theta degrees, I essentially put my pen here and I imagine tracing around in an arc and I stop at whatever the angle is. So if it's less than 90 degrees, it's going to end up in quadrant 1. So what we then do is we take a look at the triangle, and we say, okay, what's the opposite to theta? And we see that that's actually the y component of the point. The adjacent to theta is the x component. So then the question comes, well, what do we call this arm? And if we imagine this arm rotating around, we trace the point, we get a circle, and this arm would be the radius. So we call this r. And since we're given point x and y, and we calculate r with that, and we know that r squared is equal to x squared plus y squared, so r is equal to the square root of x squared plus y squared, we know that r is always going to be greater than 0. So r is always positive, and this is very important. So once we've done this diagram, we can now redefine sine, cosine, tan in terms of x, y, and r. So sine becomes y over r, cos becomes x over r, and tan becomes y over x. So let's scroll down here and let's do two questions which are just related slightly. So question 1. We want to find sine of, let's say, 30 degrees. Now we know sine of 30 degrees is 1 over 2. We've worked with this enough that we know this. But let's actually visualize sine of 30 degrees using this rotational angle idea. So if I go and trace this out, and I imagine making an angle of 30 degrees starting at my initial arm and rotating up, I know 30 degrees arm is going to be somewhere around here. And then I make my right triangle by drawing a perpendicular line to the x-axis. So there's my nice right triangle. And 30 degrees right there. So now, it'd be nice if I had this x and y point. And it turns out that a 30-degree triangle, 30, 60, 90, is that special case we know so much about. So the opposite of 30 is 1, the adjacent is root 3, and the hypotenuse is 2. So I can very quickly see that sine of 30 degrees is going to be 1 over, oh sorry, that's not root 2, root 3. That's better. I can see very quickly that sine of 30 degrees is going to be 1 over 2. And in fact, we could actually extend this to find as well cos of 30 degrees is going to be root 3 over 2. And if we were so inclined, we could find tan of 30 degrees, which is 1 over root 3. Perfect. So that's something we already know how to do, but let's imagine we have this. Find sine of 150 degrees. Now, of course, I could plug this in my calculator as well, but what we want to do is we want to come up with a picture and then rationalize what the answer is. So again, what I'm going to do is I'm going to draw 150 degrees on this Cartesian plane. So imagine starting here at the initial arm and I rotate around 150 degrees. Well, if here's 0 degrees, when we get up to the positive y-axis, we're at 90. If I continue on to the negative x-axis, I'm at 180. So 150 degrees is actually going to be, the arm's going to stop somewhere around here. And then we notate it like this. We put an arm and we say 150 degrees. So the question then comes, well, how do I introduce a right angle triangle from this? And again, our right angle triangle is always constructed by drawing a perpendicular line with the x-axis. And the reason why it's always the x-axis is by doing this, it keeps our ratios the same. Y over r, x over r, y over x. So what I want to do is I'm actually going to pull the ratio for for sine of 150, cos of 150, and tan of 150 off of this right triangle here. So what I do first is I actually calculate the angle there, and I know that this angle is going to be 30 degrees. 30 degrees is called the related acute angle. Let's just write this over here so we have that. So 30 degrees is called the related acute angle to 150 degrees. So now what I do is I come over to my diagram and I'm going to fill out my 30, 60, 90 triangle. So the opposite is 1, the adjacent is root 3, but notice now, be careful, I'm on the xy plane, so this isn't root 3, it's actually negative root 3. And the radius is 2, and we keep that positive. So this point here is actually going to be negative root 3, 1. So the sine of 150 degrees is going to be the opposite 1 over 2. And again, I could take cos of 150 degrees. And so cos of 150 degrees is going to be, and notice, it's negative root 3 over 2 because we use the x from this xy pair. And of course, I could find tan of 150 degrees. Tan is opposite over adjacent, so it's 1 over root 3. But root 3 is negative, so it's negative root 3. So what we see here is that sine of 30 and sine of 150 are the same. And these are and 30s are called a related acute angle. So we're going to go through one little exercise just to kind of wrap up this video. And here's what I want you to do. I want you to get your calculator out and type this exactly in your calculator. Sine inverse of sine of 30 degrees. I want you to type that in your calculator and press equals. And you'll see you get 30 degrees. And that makes sense because we're applying the inverse, sine inverse to sine. So these two operations cancel each other out, so we're left with what's on the inside. Now take your calculator and type this in. Sine inverse sine of 150 degrees. Don't hit equals yet. I want you to ask yourself, what will your calculator give you as an answer? And remember, and sine inverse and sine undo each other, so the result is going to be 150, which makes sense. But of course, you press equals on your calculator is going to give you 30. And this is the reason why we have to apply this rule in the ambiguous case. Remember why we're looking at this? When your calculator takes sine of 30, it gets 1/2. And then when it takes the inverse sine, it generates 30. Your calculator is going to do the second question in those two steps as well. So what your calculator is going to do is it's going to find the sine of 150, which is 1/2. But then when it takes the sine inverse of 1/2, it doesn't know that the angle was 150. Your calculator isn't smart enough to distinguish what quadrant your angle happens to be in. So what happens is when I start dealing with angles that are larger than 90 degrees, or I start talking about what are called rotational angles, what happens is your calculator has, there are calculator regions that your calculator will work in. Your calculator will only ever give you an answer in either quadrant 1 or quadrant 4. Again, quadrant 4, we haven't actually talked about why that is, but your calculator will never give you an angle back that happens to be in quadrant 2 or quadrant 3. And that's because the calculator doesn't know which angle you're working with. So if I would take the sine inverse of 1/2, it's not smart enough to know the context of the problem. And so that's why, if we come right back up here to where all this question started, the question is, well, why do I take the acute angle and subtract it from 180 degrees? The reason why we do that is because your calculator is only smart enough to give you the case in quadrant 1. If I'm interested in the angle in this quadrant, if I'm interested in theta, or in this case, B2 could be represented like this. What happens is your calculator is going to give you the related acute angle, which is 43.5. So therefore, to find the obtuse case, we take 180 minus 43.5. This is a long video. I hope it helped. Again, this was just a quick primer. There's lots more information about this. Rotational angles are actually a lot of fun, and you can do a lot of cool things with them. So if you have any questions, please don't hesitate to ask. And good luck in all your work.